This is class 80 physics. Today I'm going to discuss about the oscillation. Now I'm Mohammad Monjur Hossain Chowdhury. I'm teaching physics for last 17 years. I got my graduation and post-graduation from University of Dhaka. I'm becoming student first class pass in my MS. And I'm going to University of South Florida in T program in USA. I become best teacher of my current school 3 times. I spent my college life in Notre Dame College. I have 2 sons and I love watching movie and traveling. Now stay with me to learn about A2 physics oscillation. The oscillation is very simple thing. I make a movement of this pendulum, of this spring system there is vibrating, it starts vibrating over there. Now, if you think, will it be continue forever? No, it's going to be stopped some time later. Maybe it takes too much long time, but it will eventually stop. What makes this thing stop there? Because some of the energy is lost. Air resistance around this system, the spring and the mass, makes the spring eventually stop there. So the oscillation is going to be decay, and today's topic is about the learning about decays. So different types of damp oscillation we are going to learn, like how this damping happened and why this damping happened, with examples and graphical presentation. After this one, we are going to learn about the natural frequency, the driving frequency, and the resonant frequency. Then we're going to learn about the graphical analysis about related with this driving frequency, natural frequency, and the resonance frequency. And later on, we're going to learn about the uses of the and the disadvantage of the resonance. Later on, we will start solving question paper that is very important for you. So let's start. Damp oscillation. So the first thing is this system, the simple pendulum, will it be oscillate for a long time? Or the teacher vibrate the scale around the table, will it oscillate for a long time? No, it's going to eventually stop because some of the energy is lost to the environment. So in that case, there is some damping happening to the oscillations. So we can come to the conclusion. The oscillation goes under decaying energy to the environment, leading to reduce the amplitude, is called damping. So if it is vibrating, the amplitude is gradually decreasing. So first, initially, you can consider this one was in this position and goes up and down this position. Now later on, the vibration from the mean position is decaying, and eventually it's going to be stopped. So we can say this damping is the amplitude decreasing through the energy loss to the surrounding. Now, if we go for the simple harmonic motion, the simple harmonic motion without losing the energy, how the graph will be looks like. For example, it starts vibrating and there is no loss of the energy to the surrounding. Now if we draw the graph will be looks like this. In that graph, you can see the amplitude is remain constant because there is no loss of energy. We don't consider that any loss of the energy. So over here, you can see all the amplitude, the maximum height or the minimum height is remain same. This amplitude is remain same because there is no loss of energy. But if there is some loss of energy, it becomes slowing down. Now after losing some energy in the graph, from the above graph, how the new graph will be looks like? If they lose some energy, the new graph will be looks like this. So in this graph, you can see the amplitude is decreasing gradually, and the time period is going to be increased a little bit more. So over here, the time period, and over here, this time period is increasing a little bit more. So there is the two things we have seen. in this diagram, number one, amplitude no longer constant is decaying, and the second thing, the time period is gradually increasing there a little bit. So we can come to the types of the damping. So what are the types of the damping can happen? Is all the damping is like that, slowly is coming to that one? Or if some are going to be stopped very quickly, or some are, it will take long time. So according to the time and the position of the damping, there's three types of damping we are considering. First one, the light damping that we explained before. So in this case, its amplitude is decreasing gradually, slowly. So this is called light damping. The second part is critical damping. The example for the critical damping is like that. I pull it down, I release and stop. It's become immediately stop the equilibrium position. So if this type of system is work, like I release from there, I pull it down and I release, but the spring come over there and stop eventually. There is no more vibration over here. So I pull it down, release, and it's come over here and stop. That will be the example for critical damping. I think you can't get that one because in realistic life it does not happen ever. So now coming to the next one, it is the heavily or over damping. Now what happened in the heavily and the over damping there? Like I pull it down, I release it, and it's come to the equilibrium position very slowly, further any oscillation. It never will happen in this case. So before giving the real life examples, I like to clarify the three types of damping: light damping, critical damping, heavily damped or over damped. So light damping, the amplitude is decreasing gradually. The critical damping, the amplitudes come to the zero as quick as possible, and over damping, there will be no more oscillation and it will come to the zero, but it will take longer time than the critical damping. Now graph, if you see the graph over there, you can understand which one is the overly damped, which one is the critically damped, and which one is lightly damped. So the first one, this one is lightly damped because the amplitude is decreasing gradually, and this one is critically damped because it's coming to that zero position. And overly damped is like this one. It takes too much time to become at rest. So we have learned about the three types of damping. Now we go for the real life example. Number one, I think you have already know about the real life example of the first one. Light damping is like a spring mass system. It's example of light damping. There is an example of light damping I have mentioned before earlier, the simple pendulum. That is the light damping. Then you can go for the graph of the light damping. The amplitude, if you see the question, the amplitude is decreasing like this way. So you can say this is light damping. So we can go with the critical damping. In the critical damping, is that one is the like a car absorber. Because if you ride on a car and the car is going down, there is a bumping is happening. And if you start bumping, no, you don't like that car. It should be smooth. So you need some shock absorber. So when it's the bump, it comes to the rest immediately. So you don't feel the bumping over there in the road. So if you have a shock absorber in your car, a good one, you will get the less bumping. So that will be the more better car. Now in this part, there is a bumping is happening, but due to the critical damping, the car is come to the zero position very quickly. Look at that graph. It comes to the zero position very quickly. One thing you have to remember, this graph is usually less than the half of the t is better. So if the time period is less than half t, so it comes quickly, so you will not feel any oscillation over there. So it is more stable there. Now the last example, overdamping, like our door system, like the hinge in the door, automatic door closer. So in that part, you can see the door is closed and open. But when you use the hinge over there and the door closer, you open it and it closes very smoothly. That is overdamp. It doesn't make the oscillation once again and again, but it makes the oscillation without any oscillation. It's come to the position. So that is the overdamping happening is over there. So in overdamping, you can see the graph is started from there and it slowly gradually come to the equilibrium position. So we learned the three things over the real life example there. Your speedometer in the car is also the overdamping, like not overdamping, sorry, critical damping. Like your speedometer is like when you accelerate, it's immediately gear up and come to the zero again. So when it is getting the acceleration, and it's coming back again to the zero. So that is very critically damping. So your speedometer is actually the critically damping. So it's come to the zero again and again and there. So now the next part is about the resonance or the frequency. About we know that how this frequency is working. So everyone enjoy this part, right? When you were a child, everyone, none of them was missed with this type of swing over there with the friends. Now in this case, the girl have a swinging and there are friends to push her. So in this case, look at that, they gently push her over there gradually and her swing rate is increasing. So then, yes, they push her properly and they go more high. It's going to be more high. Look at that last part. They are not able to catch her to give the force, so she should fly away. So everyone have enjoyed this high flight and the high enjoyable swing over there. And there is a physics over here. Like they are giving her the perfectly swing there, perfectly force are giving there. So she get that force. With that force and her own force, they are combined together, and both together, the little kid is giving some forces there, and she has her own force. Both together, she is going flying high. So this is called the resonance. Before understanding the resonance, we have to go about some definition. So these people are giving the forces to them. We call that one driving force. So if something is giving some forces to the system, we call this driving force. Now the driving force creates the frequency to that system is called driving frequency. Then what is the resonant frequency? If driving frequency and the natural frequency are equal, then we call this resonant frequency. Now the thing is, as a student or as a teacher, I gave you perfect homework, perfect classwork, up to the mark, difficulties level of the questions to you, and I'm giving some load to you. So as a teacher, I'm pushing you down there, and as a student, with your own potential, you are receiving this thing. Now, when my force and your own potential is matched, you will achieve much better progress. But if I continue giving more force, which you cannot get absorb that thing, you cannot improve. Or it can be happen the reverse way, like you need more force, but teacher is not giving up to that level of effort, you cannot get that one properly. So to get a good result, you need the resonance frequency there. So now over here, driving frequency is the frequency is given by the outer source. Oh gosh, this, and We're coming back right now. So it has to be equal. Now, if we see what is resonance, the resonance is describe the phenomena increased amplitude that occurs when the frequency of periodically applied force is equal to close to the natural frequency and of the system on which acts. That means the natural system frequency of the natural frequency and the external forces is given, then the amplitude is going to be boosted up. That is called the resonance. What is the natural frequency? If you take this one as to be vibrate, it vibrates its own system. No external force is given. It is vibrating its own. If you take the stopwatch here, and if you count the time period and calculate the frequency, you will find every time it is same. Now, if you pull it down more and vibrate like this way, the time period remains same. So the frequency, if you move it very slowly, the oscillation is like that way. If you measure the time, you will find it is still same. That means it has its own frequency. It depends its mass and the spring constant to vibration of that particular frequency over here. So in the particular frequency, in the driving force, if it reached the resonant frequency, the amplitude will be boosted up. Alright. So what is the natural frequency? The natural frequency of an object, if without any force, without any external force, the oscillations is called the natural frequency. So we're coming with the advantage of the resonance over there. Number one resonance over there is advantage. It's a microwave oven is heated up the water molecules with a particular resonance frequency. So the only water molecules heated up, so your food warm very quickly. So like radio signal, when you pick up a radio signal there, you adjusted the resonant frequency so you can get that one particular radio station. In MRI, they are just make the hydrogen adjusted with the particular range of radio frequencies, and the MRI is performed. So there is lots of uses are the resonance over there, like the playing musical instrument. So these are the advantages over there, but there is some disadvantage over there. Number one, every mobile phone, I think most of the mobile phone have the airplane mode, that is turn off the mobile phone. So no ringing, no signal is going there, because sometimes the mobile phone signal interfere with it is interference with the cockpit signal with the station. They are talking with the pilot, talking with the radar station, the position station. So for that reason, the resonance can be disturbance. Maybe the pilot will miss the signal over there. So there is another one is the catastrophical happened there with the earthquake, but the building construction, its own resonance frequency, if matched with the seismic wave of the earthquake, there will be maximum amplitude of vibration, so it's going to be collapse. You know the wine glass can be broken down by making the sound. So because the wine glass have a particular frequency, natural frequency, if the sound is also have the natural frequency, so amplitude will be maximum, it will be broken down. Some bridges, like the soldier don't march over the bridges, because if they walk over the bridges over there, the resonance can be created, the bridge can be collapsed over there. So these are the disadvantages over there. So how we can reduce this resonance there? So damping is helping. So like if this vibration is become more vigorous, so what I can do, I can add some feather over there, so more resistance. If there is some vibration happens in the viscous liquid, I can intensify that liquid intensity, so it will make more damping over here. So what will happen? If damping increase, then the resonant frequency decrease, maximum amplitude decrease, the peak of the amplitude become wider. So it will be looks like that. If I increase the damping there, so from the top, no damping, now they are under damping. We increase more damping. Now check that the frequency, the resonance frequency has been shifted when we add the damping. And remember, this become more wider. It's become sharp, but this part is become more wider. Remember, none of them is become zero in this driving frequency of that part. So we go to the important part. There is the solving question paper. So to solving question paper, we are going to choose a paper 4 and Cambridge paper 4 and October November 2018 4-2, and we are going to do this one with the question number 4. So before giving thanks, we love to solve the question paper right now. Okay, so here we go with the question paper. Now you can see the question over there. I have already kept over there. So this is the question there. So a U-tube containing a liquid as shown in the figure 4.2. So this is 4.2. A liquid has been poured over there, and they have their vibration inside the liquid. There is oscillation inside the liquid. So the total length of the liquid is given L. So here to there, total length is given L. The column of the liquid is displaced so that the change of the height is liquid from the equilibrium position to each of the arm of this thing is X. So there is the X column of the liquid has been changes there as shown in the figure 4.2, because this is question number 4. So they label CAIE, Cambridge label their question figure 4.1 because it's question number 4, figure 1, and it's question number 4, figure 2. So now there is the liquid in the U-tube oscillation in such a way, the expression has been given. G is the gravitational field strength, so we know that one. So we have to just find it out. The number 1 is show that the liquid column undergoes simple harmonic motion. In the last class, the previous classes, I have discussed about how these the simple harmonic motions work over there and definition of this one. So now, right now, I'm going to write about how this thing works. Now here, G is constant. There is a G is constant, and also L, the length, is also constant. So if both of them, G and L, both of them constant, so you can easily write twice G by L definitely will be a constant. Now in this part you can write this acceleration is equals to some minus some constant value of the product of X. X is here is the displacement of the water liquid. Now you can see that one is A must be directly proportional to the displacement, and direction is the opposite as this is going. So you can write so the liquid column goes, the liquid column, beg pardon, COL is there. Liquid column is undergoes, we write simple harmonic motion. So this is the way how we can say this thing. But remember, there is a formula has been given over there. So for better understanding, you have to review the first class over there on the simple harmonic motion. This harmonic motion, the first class one. Now here is the graph. So there is a graph has been given over there. So this is the, you can understand it's a light damping, and it starts from the 2 and it's going to damping over like this way. Okay, so they ask this, what is the length of the liquid over there? So in this graph we can calculate, from this graph we can calculate the time period is T. How we can calculate? So starting from this part and it's finished at 50. So one wave is completed from there, and there's another, this wave is completed over here. So the one complete wave is the time period T. So from this graph, we can calculate the t over there, and you already know t equals to omega. T is given by omega equals to twice pi by t. So you can easily calculate this part. So like t equals to twice pi by omega. Omega is the angular speed there. Now you might ask the question why we are finding out this one, because we are going to compare the equation later on there after a few minutes. So you can calculate the omega square. If you make the subject the omega over there, you can write 4 pi square divided by t square. So this is simply taking the t over there, omega over here, and take the square on the both sides. So you will find that t omega is there, because a is given by minus omega square x, and in this equation a is given by minus twice g by L. So if you compare the two equations, if you compare these two equations, so you can easily calculate the L over there. So you can make the L is nothing but the L is given by twice g by omega square. By comparing equation 1 and the equation number 2, you can easily calculate that one. So from there, you put the value over there. So omega square you know already. So if you put the value, it will be twice g t square by 4 pi square. Put the value 2 into 9.8 into 0.50 whole square divided by 4 by pi square. You will get the length is approximately 0.12 meter there. So this is the part where you can compare the equations, the simple harmonic motion equations there. Okay, so we just continue with the question over there. Now there is the damping is coming over there. So just one of the damping, what things makes is damping over there. So if you see the question in the beginning, so you can see there is the system is vibrating over there. So there is some friction is happening there. Or you can say there is some viscosity of the liquid that makes the damping over there. So all of the question, all of the answer that comes out in your mind will be right, because we talk about the friction. So if you write the friction of liquid with the wall, or you can write the viscosity of the liquid, because if this is condensed thing, so that will be also the viscosity of liquid. Also one of the reason why this is become damping over there. Now they talk about the total energy after completing this one. So in oscillation in lecture number 2, we have talked about the energy over there. So the energy, total energy, we have write the equation is half m omega square is the maximum amplitude square. That is the total energy. So we were going to put this energy over here, and now for 1.5 complete oscillation, if you go through that 1.5 complete oscillation from the graph, there is a 1 complete oscillation and 1.5 complete oscillation is happening here. So here is the first complete oscillation. So there is the 1.5 complete. So here to here is 1.5 complete time over there. So now you can go through there, you can get there 1.3 over there. So it's minus sign, no problem with the minus. Put the minus over there. And for initially, in the beginning, it was plus 2 over here initially. So let's check the question, what they're asking for. So they say that this is the energy you have to calculate over there. So total energy, and the total energy is given there. So let's solve this problem. So I know that total energy is given half of that one. So let's put the value there. So we put the value and we get the answer. So it is half of mass of the liquid and omega square, and x naught is the maximum 1.3 whole square. The omega square angular speed will remain same for the system, so I'm not putting the value over there. And there is the again half of m is omega square, and it is 2. So all these values are gone away, they are same, so we can write there the answer will be that square divided by that square. This answer is 0.42. This is the ratio, so no unit are going to be used. 0.42 will be the answer. So this is how we are going to solve the question paper over there, and this is going to how we are going to practice this thing. So I'm going to upload the homework in your accounts over there, so you will get the homework there, and I will keep you the pressurized in such a way like the resonance result will achieve. Before leaving the class, I'd like to specially thank you to watching the video over there, and I'm going to special giving thanks to the BAC International Study Center because to arrange this wonderful class with you. Thank you everyone. Thank you very much. Stay tuned with Monjur to learn more about physics. Thank you.